Okay, let's take a look at the next section in our textbook, which is on hyperbolic functions today. And I'll go ahead and open up the slides and get a full screen view here. So section 3.8 is on hyperbolic functions. I want to first discuss a little bit about what is a hyperbolic function. We'll talk a little bit about their properties after we introduce them. And then we'll talk about the hyperbolic tangent and then derivatives of hyperbolic functions. Okay, what is a hyperbolic functions? Well, it turns out that two combinations of e to the x and e to the negative x are so common in practice, especially in engineering, that they're given special names. They're called the hyperbolic sign, denoted the sign hyperbolic or hyperbolic sign, S-I-N-H, and the hyperbolic cosine, denoted C-O-S-H. So these are the two functions. Well, what are they exactly? And here's what they're defined to be. The hyperbolic sign is e to the x minus e to the negative x all over 2. And the hyperbolic cosine is defined as the function e to the x plus e to the negative x all over 2. So you can see the difference between the sine and the cosine is just a difference of whether or not I have a difference on top here or a sum on top here in the cosine's case. So let's take a quick look at what these hyperbolic functions look like. So I'll go to the Desmos link and we'll take a look at this. So we can see that right now, let me put it in projector mode. We can see right now that we have a function that is e to the x minus e to the negative x all over 2. So what do we have here? We have, let's going back to the slides really quick. We've got the hyperbolic sign shown there. Okay, so let's go ahead and get out of there and come back. Let's take a look, turn that one off and do the same function as above, but with a sum, and I can see there's the hyperbolic cosine, which interestingly enough looks somewhat like like a parabola. It might be worth at least sort of inspecting a parabola that's close to this particular function. One way we could do that is we could put a new function in here, though I don't know, let's call it n of x, which is just equal to some ax squared, where I'm going to make a slider for a, and then I'm going to add 1 to it so that it has the same y-intercept as this hyperbolic cosine. So I'll add the slider and just kind of look at what happens here, and you can see that indeed the hyperbolic cosine and the parabola are not the same things, that no matter how close I get here to adjusting it, I get some difference in curves. And yeah, it turns out that the hyperbolic cosine is not a parabola, although it sometimes is mistakenly assumed to be one. So I guess the purpose of this is just to show you that indeed it is a different object than a parabola. It turns out that this is actually a shape that we see quite often in engineering. Inverted, this shape is the shape of the St. Louis Arch, for example. That's a hyperbolic cosine. Also, when we hang, I guess, elements that suspend bridges, often what we're looking at there, you know, if you think of, say, the San Francisco Bridge and the large cables that suspend the bridge, we're looking at these hyperbolic cosine curves rather than what appears to be a parabola. One interesting thing is to note that these guys are related, of course, to the functions 1/2 e to the x. So we can see that as x gets large, the term that dominates here, of course, will be e to the x, because e to the negative x for large x is very small. Conversely, we can take a look at the fact that 1/2 e to the negative x is the function that dominates in the hyperbolic cosine as x gets very small, and that's just for the converse of the reasoning I gave before. And then taking a look here, let's see, I've got one more term. Oh yeah, this would be negative 1/2 e to the x. If I turn off the hyperbolic cosine and I put on the hyperbolic sine, I can see that's what's dominating, I guess, in the sense as the hyperbolic sign is getting extremely, I guess, as x goes to negative infinity, the dominant term, I guess, on the hyperbolic sign would be the second term because, well, if you take the opposite of a negative, it gets large, and we're negating it, so that means that the function is going to negative infinity as x goes to negative infinity. So it's certainly some relationship, but I guess the thing you should be familiar with is that how these things look. It looks like the hyperbolic sine is what we would call an odd function. It's symmetric about the origin. And the hyperbolic cosine looks like what we would call an even function because it's symmetric about the y-axis. So we'll take a look at that in our study. There they are, the two functions superimposed. Okay, well, let's go back and take a look at our slides again. So we've got some properties of hyperbolic functions, and the first one we want to take a look at is, well, what is the hyperbolic sine of 0? So we have this property that the hyperbolic sine of 0 is 0, and another property that the hyperbolic sine of the opposite of x is equal to the opposite of the hyperbolic sine of x. So this would just simply be a demonstration that the hyperbolic sine is an odd function. And this would be a demonstration that the hyperbolic sine passes through the origin. So let's go ahead and take a look at that, and we'll see if we can prove it. So I'll go ahead and switch to a piece of paper here. So the first thing we need to do is write down, oh, just what is this hyperbolic sine, right? What does this thing look like? Let me pull out my pen. So we know that the hyperbolic sine is defined as e to the x minus e to the negative x all over 2, right? So that's the definition of the hyperbolic sine, and what we'd like to show, what we want to show is that number 1, the hyperbolic sine of 0 is 0, and number 2, that the hyperbolic sine of negative x is equal to negative the value of the hyperbolic sine of just plain old x. So this thing is an odd function. Okay, so let's go ahead and get after it. So for number 1, well, let's just simply plug in 0 into our hyperbolic sine function. We get e to the 0 minus e to the negative 0 all over 2. Well, that's just the same thing as 1 minus 1 all over 2, which is 0 over 2, which is 0, and we are done. So indeed, the hyperbolic sine does pass through the origin. Just plug it in and verify. Let's see, so for number 2, let's take a look at that one. What we want to show is that the sine, hyperbolic sine of negative x is equal to the opposite of the hyperbolic sine of x. Well, let's just go ahead and plug and chug. So if we plug in the negative x value into the definition, we get e to the negative x minus e to the negative x all over 2. Okay, well, let's check what that means. That's e to the negative, not z, but x. E to the negative x minus e to the x. Okay, that's all over 2. Now, keeping the eyes on the prize, what we want to show is that this is the opposite of the hyperbolic sine. So what we'd like to end up with is an expression like this one up here with a negative sign out in front. So that's what I'll do next, is I'll factor out a negative 1 out of the top expression. What that means is that the first term must be negative e to the negative x, and the second term must be plus e to the x. That's all over 2, which means I have the opposite of, now rearranging because addition is commutative. On top we have e to the x minus e to the negative x all over 2, and I recognize this as the definition of the hyperbolic sine of x. So that means that this is equal to the opposite of the hyperbolic sine of x. And we are done with that little demonstration. So indeed, the hyperbolic sine passes through the origin, and it is an odd function, and we can move on. So I'll get out of here, minimize this, come back to our slides, and talk about some other properties of hyperbolic functions. Let's take a look at the hyperbolic cosine and see if these two results are true. Is the hyperbolic cosine of 0, 1? Well, what this really means is that it has a y-intercept. The function has a y-intercept of 1. And is the, I guess, the hyperbolic cosine of the opposite of x equal to the hyperbolic cosine of x? So this statement would just be a demonstration that the hyperbolic cosine is indeed an even function. So let's go back to pen and paper and take a look at those two cases. Let's get something a little bit bigger so you can actually see it. Okay, so move this out of the way and get myself going here. So let's remind ourselves what the hyperbolic cosine is. The hyperbolic cosine of x is going to be e to the x, in this case plus e to the negative x all over 2. This is that parabola-looking function. Some people call this a catenary. So let's go ahead and see if we can prove the first one. Number one, what we want to show is that the hyperbolic cosine of 0 is in fact 1. Okay, so here's our proof of that assertion. Well, I think it's a direct proof here. It's just a hyperbolic cosine plug-in. Here we would get e to the 0 plus e to the negative 0 all over 2. Well, that's the same thing as 1 plus, well, e to the negative 0 is just e to the 0, so it's 1 plus 1 over 2. We get 2 over 2, which is 1, which ends our proof. Okay, well, that was easy. See, number 2, we were going to try to prove that the hyperbolic cosine is actually an even function. So the hyperbolic cosine of the opposite of x, if we can show that this is the same thing as the hyperbolic cosine of x, then that means that the hyperbolic cosine as a function treats x and its opposite the same, implying that y is the line of symmetry for the function. So let's see if that's true. So we get e to the negative x plus e to the negative x when I plug in, I guess, opposite of x. And that's all over 2. Well, so e to the opposite of x plus 2 negatives here combine under multiplication to make a positive. And I put that over 2, which is the same thing as e to the x plus e to the negative x by the commutative law of addition. And we end up with something that looks exactly like the hyperbolic cosine of x. So what we've shown is basically that the hyperbolic cosine is indeed an even function. Okay, well, let's see what else we can prove here. So it turns out that there's a analogous, you can see why these were actually named using the term cosine and sine, because all of the analogies with trigonometry, you make sure that you get these in a separate category in your brain from the trig functions, but perhaps think of them in sort of a structural sense as sharing some similarities in terms of identities, for example, like this. So supposedly the hyperbolic cosine squared of x minus the hyperbolic sine squared of x is equal to 1. Very similar to the Pythagorean identity in trigonometry. The big difference, of course, is being the minus here. So let's see if we can prove this particular result and go back to our pen and paper here. So what are we trying to show? Well, we're trying to show, what we want to show is that what we want to show is that the hyperbolic cosine squared of x minus the hyperbolic sine squared of x is equal to 1, right? And again, I think our proof is just a direct one. We'll start with the left-hand side and see if we can prove that it's equal to the right-hand side through a series of algebraic manipulations. So we have the cosine hyperbolic squared of x minus the hyperbolic sine squared of x. Well, let's apply the definitions here first. So the first thing we would have is e to the x plus e to the negative x, right? All over 2, that quantity squared. And then we'd be subtracting the quantity e to the x minus e to the negative x is what I wanted to write there. E to the negative x over 2, that quantity squared. Okay, well, looks like I'm going to have to square things out and combine like terms, put it over a common denominator if I want to get to 1. So let's go ahead and get that started. One of the things I notice is that both of them in turn include a 1 over 2 squared in both of these terms. So what I'm going to do is I'm actually going to pull out the 1/4. So I'll put that out in front, and what that leaves inside then is something that looks like 1/4 times e to the x plus e to the negative x quantity squared minus e to the x minus e to the negative x quantity squared. Squaring out those two binomials is going to give us a whole bunch of terms, but let's go ahead and do that now. So again, I'm going to have e to the 2x when I square that, and then the cross product will be e to the x times e to the negative x. Adding the x's, I get just a 0, so one cross product will be 1, another cross product will be 1, so I just get 2 in the middle here. And then squaring out the last term, that'll be e to the negative 2x. So that's the first binomial squared, I guess, if you want to think of it like a binomial. And the second binomial squared will be very similar. We'll get e to the, let's see, 2x, and then minus e to the x times e to the negative x, which would be a minus 1. And that happens twice, so we'd get minus 2. And then the last term would be e to the negative 2x, and that quantity is now totaled. Okay, so we've got that, I guess, expression at this point. I'm looking favorably on it because I see the negative is going to get rid of a whole bunch of cancellations of like terms. So I think I'm on the right track. I've got 1/4 times, let's see, so e to the 2x minus e to the 2x, those guys go away. So those guys cancel, I guess. I shouldn't call them a 1. They just simply cancel. That's the first cancellation is what I meant by the 1. And then I have an e to the negative 2x. I'm going to subtract an e to the negative 2x, so those two guys cancel and are gone. And I end up with 2 minus a negative 2, so I end up with just 4, which when I take a fourth of that is just 1. So we have indeed proven the hyperbolic identity here. Cosine squared of hyperbolic cosine squared of x minus the hyperbolic sine squared of x is equal to 1 always. So let's go ahead and get out of here and get back into the fun. So what about the hyperbolic tangent? Well, in the similar fashion to the trigonometric definitions, the hyperbolic tangent is just the ratio of the hyperbolic sine to the hyperbolic cosine. So just the sine argument in the numerator up here over the cosine argument in the numerator down here. Of course, the two 2's will cancel when we divide one by the other. So this is the resulting expression. Let's go ahead and talk about derivatives now. It turns out that the derivative of the hyperbolic cosine of x is equal to the hyperbolic sine of x, and we should probably try to prove that. So let's go ahead and prove it. So I'll go ahead and get looking at the derivative of the hyperbolic cosine of x. So here we go. And what we'd like to show, like to prove, is that the derivative of the hyperbolic cosine of x is equal to the hyperbolic sine, of x. So this is what we want to show. Okay, so again, the proof is direct and straightforward. We'll start with the derivative definition of the hyperbolic, we'll start with just the definition of the hyperbolic cosine in the argument of the differential operator. So I'll put the definition of the hyperbolic cosine, which is just e to the x plus e to the negative x all over 2. So now let's think about this a little bit. We've got a constant of 1/2 being multiplied, so that can come out in front of the differential operator. So we'd have 1/2 times the derivative of e to the x plus e to the negative x. Now I've got a sum of two functions, so I can apply the differential operator to those two functions. So it'll be d by dx of e to the x plus d by dx e to the negative x. I should probably use curly brackets just to make sure you're following. Okay, so the derivative of the exponential function, of course, is just itself. So we've got 1/2 times e to the x. And then here we would have to apply the chain rule to deal with the negative x up there. So we would think of this as an f of g of x. We take the derivative of the outside function first, which is the exponential function, raised to the inside function. Okay, so there it is. And then we would take the derivative of the inside function, I guess the operator inside of e to the x, or the function inside of e to the x is e to the negative x. Its derivative is -1. So it looks like what we get out is 1/2 e to the x minus e to the negative x. Well, that looks pretty familiar. That's e to the x minus e to the negative x over 2, which is just the hyperbolic sine of x. And you can kind of see where this really happens. The reason that that it results in a hyperbolic sine is really due, the change in sign right here is really due to the chain rule, right? If we didn't know the chain rule right here, uh, then we'd be in trouble, right? So it's the chain rule that actually brings the negative sign out in front and literally makes the derivative, I guess, happen. So that's the relationship the hyperbolic cosine has as derivative the hyperbolic sine. I guess we should probably go one step further, and sure, the hyperbolic sine actually has as its derivative the hyperbolic cosine. So in this rare case, we have an invertible differential, meaning that the derivative of the sine is hyperbolic sine is the hyperbolic cosine, the derivative of the hyperbolic cosine is the hyperbolic sine. So let's go ahead and talk a little bit about how this would look. So I'll go ahead and bring us back to pen and paper and talk a little bit about this. Now, it seems like we should be able to follow something very similar to this, what we just did for the hyperbolic cosine. So let's go ahead and do so. Let's take a look at the derivative of the hyperbolic sine of x. Well, that's just going to be the derivative of the definition of the hyperbolic sine, which is e to the x minus e to the negative x all over 2, which in similar fashion to last time, if I take the 1/2 out in front, I'm going to have the derivative applied to differential operator applied to e to the x minus the differential operator applied to e to the negative x, which is going to give me a 1/2 out in front and e to the x here, and then I'll have a minus e to the negative x times by the chain rule the derivative of negative x. So we get again e to the x plus e to the negative x all over 2, which is of course the definition of the hyperbolic cosine of x. So we're done there as well. So hopefully this is making good sense. We've got a definition for the derivative of the hyperbolic sine. Let's go ahead and do some examples to finish out. Let me count. Let's see how many I have to look at my. Looks like I got 3 examples. So we'll go ahead and start with the derivative of x squared times the hyperbolic cosine of x. So let's go ahead and take a look at that guy. Make this a little bit bigger for you all. All right. Well, so let's think about this. Example 1. If we know that f of x is equal to x squared times the hyperbolic cosine of x, what do we want to find? We want to find the derivative of that function. So the first thing I notice is that I've got this thing written as a product of 2 functions. So I'm going to have to apply the product rule. And the product rule says take the first, right, times the derivative of the second plus the second, hyperbolic cosine, times the derivative of the first. Okay, so let's go ahead and carry out the algebra now. I guess first carry out the derivative. So the derivative of the hyperbolic cosine, easy one to remember, it's the hyperbolic sine of x. We just proved that. So this piece is done, and then I have the hyperbolic cosine of x, and then I have to take the derivative of x squared, which is going to be 2x. So as an answer, I guess what I get is x squared times the hyperbolic sine of x plus 2x times the hyperbolic cosine of x. Of course, you could factor out the x if you'd like, but this would be perfectly fine answer for me. I'd kind of like to look at how Desmos confirms this, so let's go ahead and escape out of here, run into Desmos, and take a picture of this. So I need to sign in here first. Let's go ahead and take a look at the derivative function. So I'll go ahead and open this graph, and let's take a look. I think I have the hyperbolic cosine here. So let's see, it's x raised to the second times the hyperbolic cosine of x, right? So interesting, this is what this thing looks like. Really a flattened out parabola. And I can see that when I'm looking at the derivative, what I'm looking at is a derivative that's, I guess it looks kind of like the situation where we have a fourth degree whose derivative is a third degree polynomial. Huh, that's very interesting to me. I hope it is to you. So fourth degree would be, this guy, and this thing kind of looks like a third degree polynomial. So if we wanted to sort of plot this guy all out, then we'd have this sort of a situation. Like, kind of curious what this looks like there. Okay. So yeah, it looks like that's what we have. And we think we have an expression for the derivative, and that expression we think is, let's see, f, g, and h are taken, so why don't we do a j of x, our expression for the derivative, which we hope will match this orange derivative function that's drawn, x squared hyperbolic sine of x. Okay, so that's x squared hyperbolic sine of x, but we've got to add to that 2x times the hyperbolic cosine cosh of x. And bingo, it looks like we did get it when that j of x is overplotted on the derivative function that I have drawn, and indeed does seem to overlay. So that indicates that we most likely have found the derivative of the function we were curious about. Okay, so let's go ahead and move on from this one. Let's take a look at the natural log of the hyperbolic cosine of 1 plus x. Again, let's let the theory lead us, and then we'll use the graph to verify. So we'll switch over again here to my picture desk. Okay, so let's see. This is example 2. We got g of x equal to the natural log of the hyperbolic cosine of 1 plus x, and what we're after is g prime of x, right? So we've got something in the form, I guess it's sort of like a triple chain. We've got a function who has inside of it another function that has inside of it a third function. So we know how to handle chain rules. What we do is we take the derivative of the outside. So the derivative of the natural log is 1 over the argument inside it. So let's see, the hyperbolic cosine of 1 plus x. Okay, so that's the derivative of the outside function. Now we take the derivative of the argument of the outside function. So the derivative of the cosine, hyperbolic cosine, well, that's just the hyperbolic sine, right, of the argument in there, 1 plus x. And then, of course, we'd have to take the derivative of what's inside of the hyperbolic cosine function, which is 1 plus x. Turns out the derivative of 1 plus x is just 0 plus 1, so 1 is all we'll need there. So I'm getting for an answer here the hyperbolic sine of 1 plus x all over the hyperbolic cosine of 1 plus x. And we know that the ratio of the sine to the cosine in a hyperbolic setting is just the tangent. So we could just call this the hyperbolic tangent of 1 plus x as our derivative. Let's go ahead and see if Desmos backs us up. I'll go ahead and escape out of here, run into Desmos, take a look at what we've got. Ln of the hyperbolic, what was it, cosine, yeah. So cosh of x. And then we wanted it to be not just x, but 1 plus x, sorry. 1 plus x, okay, so this is sort of what we got going on here. We've got this function that sort of comes down like this and up. Oh, it's really interesting. So it's very linear. The function itself is very linear in a sense that, let's just pause it right there. Oops. Let's just get rid of this really quick, and this, and this, and this. So this is our function in question, very linear until I get in here and then curve, and then very linear once I get out. So we'd expect the derivative to be negatively valued, transition to 0 around 1, and then positively valued and pretty constant once I'm out here. And I think that's what we're seeing when we bounce a point along this function. We can see that it does definitely have some sort of a negative positive. Looks like it's toggling between -1 and 1 in terms of the value of the derivative. It's moving pretty fast, so let's slow it down. And if I plot those values, so about -1, there the derivative is valued at 0, and here we're up to somewhere in the neighborhood of +1. And so if we take a look then at its derivative, which we think is the hyperbolic tangent, so I'll do tan hyperbolic of the argument 1 plus x, what do I get? Let's go ahead and plot it. And indeed, that is the derivative that we were after, it looks to be anyways. It'd be nice if I could make that a different color. Let's make that a black. And let's make all of these blacks, just so we can tell the difference between the function and its derivative. Yeah, so the black function would be the derivative of the red function, and it's of course measuring the slope of the red function at the point A. So the red point A, the slope there at that location is being plotted on the black function, which is j of x, the derivative of the red function. So I feel pretty good about that. I think it's good confirmation of our work. Let's go back to do one more of these. So here's a nice way we can sort of now try to prove what the derivative of the tangent function is as our last step in today's lecture. So let's go ahead and see if we can get that done. I'll go ahead and switch over again to my my bigger picture of paper. And what do we want? We know that h of x is going to be equal to the hyperbolic tangent of x, and what we really want to know is, well, what's the derivative in this setting? Well, that's going to be the derivative, d by dx, of the tangent of x, the hyperbolic tangent of x. So let's just kind of think of that as the hyperbolic sine of x all over the hyperbolic cosine of x. And I guess I'll just pause right now and let you think, before I dive in, decide to yourself what you would do if you were faced with this task. Okay, well, what I would do if I was faced with this task is I would go ahead and recognize that this isn't a setting where I have the ratio of two functions or the quotient of two functions. So what I would do is I would apply the quotient rule here. So that would be the bottom function, the hyperbolic cosine of x, times the derivative of the top function. Well, the derivative of the hyperbolic sine of x is the hyperbolic cosine of x, okay? So that's bottom times derivative of top. And then I would subtract the top, the hyperbolic sine of x, times the derivative of the bottom. Well, the derivative of the hyperbolic cosine is, of course, the hyperbolic sine of x. And then that would be all over the bottom, the hyperbolic cosine of x, quantity squared, right? So this is just an application of the quotient rule, and we have a derivative, but we can simplify it a little bit. Perhaps you notice that on top what I have is the hyperbolic cosine squared of x minus the hyperbolic sine squared of x, and that's all over the hyperbolic cosine of x, quantity squared. I guess let's get rid of all these parentheses and just call it the hyperbolic cosine squared of x. Okay, and then what I notice is that I can do a couple different things here. I could notice that this is the same thing as if I distribute the denominator left and right, it's the same thing as 1 minus the hyperbolic sine of x over the hyperbolic cosine of x. So it would be where they're both squared. And then that's the same thing as 1 minus, well, the sine to the cosine, that ratio in a hyperbolic setting is just the hyperbolic tangent of x. Of course, we've got to square it. So that would be one path to a derivative. But it turns out some of you might have noticed too that there's another path to derivative or a simplified expression. We know that the hyperbolic cosine squared of x minus the hyperbolic sine squared of x is equal to, that's equal to 1, right? So this is the same thing as 1 over the cosine, hyperbolic cosine squared of x. And so that's kind of an interesting thing, because what we've really shown is that these two guys must be equivalent expressions. So those are equivalent expressions. So there's a little identity there that we just discovered. You could run through I guess, the calculations then to see that this is indeed the case. But another, I guess, example where the hyperbolic setting for cosine and sine is really similar to the trigonometric setting. I will just say that this is the one your book provides, but if intuition led you to this one, that's a perfectly good expression for the derivative of the hyperbolic tangent, and it is certainly equal to that one, and we could prove that as well if we'd like. Okay, well, this pretty much concludes our discussion. I'll go ahead and quit out here, and I look forward to seeing how you do on your homework on this particular topic.